Welcome back. So in this 49th lecture, I'll start with a numerical problem based on center tap transformer, center tap full wave rectifier. Look at the statement of the problem. It says a 230 volt 60 hertz voltage is applied. What I have written here, although it is not clear, it is applied. A 230 volt 60 hertz voltage is applied to the primary of a 5:1 step down center tap transformer. So it is mentioned that it is a center tap transformer used in a full wave rectifier. Very first thing, that a transformer is used and some voltage is applied to it, to the primary of it. So let me draw the circuit of it first of all. For a center tap full wave rectifier, we have done this many times. So the circuit is like this. You have a center tap transformer with a primary winding. I assume this to be a primary winding of this, and then you have a secondary winding which is center tapped. Say it is something like this here, and you have two diodes here. Say this is diode D1 and this is the identical diode to this D2, and at the center tap you have a load resistance RL. This has been center tapped here. It is grounded at the center, assuming perfect center tap here. Now, and of course inductive core. A sinusoidal voltage is applied here. Some voltage is applied here. Now coming back to the problem again. A 230 volt 60 hertz voltage is applied to the primary of a 5:1 step down transformer. So first of all, the turns ratio of this is 5:1. So N1 upon N2 is given to you, and 230 volt 60 hertz is applied to the primary of this. It is applied to the primary of this. It means the voltage which is applied here is 230 volt and of frequency 60 hertz. The frequency of this is 60 hertz is applied here at the primary of this. Having a load of 900 ohm means if this is RL, so I can say that this RL is given to me as 900 ohm. I assume this as RL. If the diode resistance is 100 ohm, means if this diode is having some forward resistance, that is 100 ohm. For this, as well as since the diodes are identical, this is 100 ohm. That is the forward resistance. I assume this as RF. Whether for this or for this also RF is given to you 100 ohm. Determine the following parameters. Now before I come that what has been asked me to determine, I draw the circuit diagram. I have drawn the circuit diagram, as well as I'll draw the waveform for this input and output waveforms. Although it is not asked in the problem, but for better understanding, let's draw the input and output waveform for this. Suppose I say that this voltage, suppose I say that I name this as Vs, and the input to this, whatever I have to find out, remember that it is the input which I assume is the input between the center tap and to one end, either this end or I can say that this end. This is Vi. This concept should be very clear. And of course this Vi is half of the voltage between these 2 points. Suppose I say that this point is I name this point. Suppose I say that this is A and this point is B. And at center tapping, suppose I say that this point is C. This point or this point are the same thing. This point is C here. So let's see what happens. Initially, I am interested in drawing the waveform of this, and I'll draw the waveform for, first of all, suppose I draw the waveform, the sinusoidal waveform for this Vs. So I am drawing this Vs here. Let's draw this. Of course, this is omega t, and suppose I say that this is Vs, this Vs here, and of course it's a sinusoidal voltage of 60 hertz. So I draw a sinusoidal voltage of 60 Hertz here. I am not using a graph paper. Please assume that these distances are equal as well as this is also equal. So of course this is 0, this is pi, this is 2 pi, 3 pi, 4 pi and so on. I drop these points down here. Because I need the other voltages also, other signals also. So now it is mentioned that this is Vs. This Vs I have shown here. Now it is 230 volt. Now until and unless it is not mentioned whether it is a peak value, in general when we say an AC voltage, it is the RMS voltage. Means the RMS value of this is 230 volt RMS. This is 230 volt RMS. This is what is given here, is the RMS value of this. If I say what is the peak value of this, for example, although it is not asked, this maximum amplitude of this, the maximum value of this or the maximum voltage will be 230 root 2. 230 root 2. Now I am interested in this VI actually. What I am interested is in this VI. What is the input voltage? So let's draw the input voltage first. Of course this input voltage will be a sinusoidal one. The function of this transformer is to simply step down this. The frequency and time period will remain the same. So if I sketch this VI, I am sketching this VI with a different color. Of course this is omega t as it is. It will be a step down. Let me show it. It is a step down voltage here. This is something like this. Assume this to be of same gap. Same, that is, this is 0. Same points have been dropped down here. Pi, 2 pi, 3 pi, 4 pi and so on. Now let's find out what is the value of this VI here. This is VI. Now I can say that with the transformer turns ratio, I can say that V1 upon V2 is equal to N1 upon N2. So Vs, look at this. I can say that Vs upon completely will be step down voltage. You will get the step down voltage between this points A and B. So I can say that Vs upon VAB means this voltage upon the voltage that I obtain between A and B will be equal to V1 upon V2 is equal to N1 upon N2. So it will be 5 upon 1. Of course, value of Vs is given to me. Value of Vs is 230. So this implies that 230 upon VAB between A and B is equal to 5 upon 1. And from here, this implies that I'll get the value of VAB between A and B. Voltage between A and B will be 5 4 20 and 6 3 46. It is 46 volt. I hope that this is clear to you. Now 46 volt is between this, and since this 230 volt is RMS, so naturally this is RMS value. It is not the maximum value, but it is the RMS value. Now I am interested in VI. VI is half of this. What VI is between this A and C is half of between A and B. So VI will be equal to VAB upon 2, and that is equal to 46 upon 2, I can say. 46 upon 2. So the value of VI which I will obtain is 46, of course 23. This is 23 volt, but remember that it is RMS value. It is not the maximum value, because what I am dealing here is with the RMS value. So naturally at the output and also you will get a RMS value here. Now it means that this VI is equal to, look at the value of this VI, it is 23 volt RMS. 23 volt RMS value. This 23 volt is the RMS value. It means this 230 volt RMS value at the primary has been stepped down by the center tap transformer will give you 46 volt RMS between point A and B value, and you will get 23 volt RMS between this A and C, which is input to this diode, or which is input to this diode, which is acting as a rectifier, which is solving the purpose of rectifier. The purpose of rectifier being solved by this diode only. The function of this transformer is to step up or step down the voltage, that's all. So it is 23 volt RMS. So naturally, what is the maximum value of this? If I have to find that, what is the value of Vm? This Vm. What is the value of this? It will be 23 root 2. This value will be 23 into root 2. This is my maximum amplitude of the input signal between this point and this point, Vm. Once you have done this, rest everything is quite simple. So if you see, now this Vm is given to, so what I obtained here, this implies that what I have obtained is Vm is equal to 23 into root 2 volt, this much volts. Now let's draw the output circuit also, then I'll see that what has been asked. Next is, let's draw the output voltage. Output current I'll draw. Voltage will be of same nature. Again, this is omega t. Output will be a DC. Full wave is rectified. Working, I have told you how. So suppose I say that this is the current. I say that this is your current. Now this is representing I. Of course, IO I can say, output current, or across this load IL. Same points, this is 0, this is pi, it has been dropped down, this is 2 pi, three pi, 4 pi, let me use another color, it is 4 pi, and so on. Now the point is, of course, this is the instantaneous value of this will also be Im sin omega t. Im sin omega t, Vm sin, Vs sin omega t, Vm sin omega t, and all these things. Now next, what is asked? Similarly, you will have Vo also same nature. Now what has been asked? DC voltage across the load. So what is VDC? Look at the first part. I have to find the DC voltage across the load, means VDC. I know that VDC for a full wave rectifier, it is equal to twice Vm by pi. Twice Vm by pi. Vm, I have found that this is the value of Vm. So I can say it is 2 into 23 root 2. Excuse me. 23 root 2 upon pi. And if I calculate this, as per my calculation, it is approximately equal to 20.7 volt. This much. I want you to cross check it, please. I may be wrong also. Second part, B part, it says determine the DC current flowing through the load. What is the DC current flowing through the load? Means this DC current flowing through the loads, or the DC value of the output current. What is the same thing? I need the DC value or the average value of this. This is IDC. And I told you how to find the value of IDC for a, what is the formula for this? IDC is equal to twice Im by pi. But I don't have this Im. The question is that I don't have this Im. I know that since Im is equal to Vm upon Rf plus RL. Im in this circuit, for this, if you see, this is Rf and this is RL. Im in the circuit, Im will occur when V is equal to Vm. So Im is equal to Vm upon Rf plus RL. So I can say this is equal to IDC will be 2 upon pi and Vm upon Rf plus RL. You simply substitute the value of this much as per my calculation. Alright, I want you to do this. Maybe wrong also. Simply substitute the value of Vm is equal to this much and Rf and RL. You will get the value of IDC. I want you to do this calculation on your own. IDC. Or it is simply VDC upon RL also, you can put in that way also. Next part is DC power delivered to the load. Next part you have to find, third part is DC power delivered to the load. So PDC is equal to IDC square into RL. IDC you have calculated from here, that is this much, and you simply substitute the value, you will get this answer, how much it is. And last part is rectifier efficiency. As far as rectifier efficiency is concerned, there are two ways of finding it. Either you find it PAC or PDC upon PAC, and there is a shortcut that I can say, it is equal to 8 upon pi square. We have derived this formula. It is equal to 8. If you remember, I told you in the last lecture or last to last lecture somewhere. Yes, efficiency of a center tap full wave rectifier is 8 upon pi square RL upon RF plus RL. So it is 8 upon pi square into RL upon RF plus RL. So simply substitute the value of RF wherever it is asked. Substitute this RF is equal to 100 ohm and this RL is equal to 1000. So I hope that this is clear to you. This complete part is clear. These four parts which has been asked. One more part I want to add in this problem, that determine E part. Determine the frequency of output wave. Frequency of output signal or the rectified output. This is what you have to find, the frequency of this. Now see, the frequency of the input signal is this. Frequency of this is this, which is given to you 60 Hertz. Now look at this, what is the time period of this input signal? If you see that the time period of this input signal is 2 pi. Fundamental period we say that when it repeats. It is repeating after 2 pi. So time period is 2 pi of the input signal. On the other hand, if you see that the time period of this is pi, time period of this input signal, whether I say about this signal or of this signal, the time period of this, what is the time period of this signal? Suppose I say that the time period of this input signal, I represent this by Ti. Time period of this input signal is 2 pi. On the other hand, the time period of this input signal, of this output signal, suppose I represent this by TO for output, it is pi. Time period of input signal is 2 pi and time period of output signal is pi. The time period is halved. If you see that the time period is from 2 pi, it is changed to pi, it means the time period of output upon input, if you say, it is 1 by 2. So the output time period is just halved as compared to input. And frequency, the frequency is reciprocal of time period. You know frequency, this frequency is equal to 1 upon T. Now if the time period is halved, it means that the frequency is doubled. Output time period is half of the input time period. So naturally the output frequency will be double of this, 1 upon 2. 2 will go in the numerator. So it means that the frequency will be just doubled. So the frequency, if I say what is the output frequency, FO. This is the fifth part of the problem. Output frequency. Determine the frequency of the output signal. So the frequency of the output signal will be just doubled. It means it will be, initially it was 60, so it will be 120 Hertz. On the other hand, had it been a half wave rectifier. For half wave rectifier, just see, although it is not asked, if this is the input signal, the half wave rectifier is like this. The output of half wave rectifier is like this, if you see. This is the waveform for half wave rectifier. It is like this. This is your half wave rectifier. So the time period is same. It is repeating after 2 pi, 0, and this is 2 pi. And here also it is repeating after 2 pi only. So for half wave rectifier, the frequency remains the same. On the other hand, in a full wave rectifier, since the time period is halved, so the frequency is doubled here. So the frequency of this wave is just doubled. Initially it was 60 Hertz. Now it is 120 Hertz. So I'll stop at this moment here. Thank you for the time being.